So the title of my presentation is "Helping the Internet to Scale," and I thought this would be a good way to both say something about the company and the interesting technologies that we work with. I'm a lead of the system operations division in Krakow. We have a big office which is still growing. We have like 170 people in Krakow doing cross company like functions. We have all business units represented, so it's a pretty cool place. So first, something about Akamai. Probably not everybody, not all of you know what's this. I actually learned about Akamai by tracing one TCP connection from my internal network back in the day, downloading Microsoft updates, and that's how I found out. But it's not mostly like recognized by people using the internet because it's all only underneath. So Akamai is a network which provides like content. Like if you go on Facebook, if you download Microsoft updates, if you log into a bank, you probably don't know it, but your traffic is accelerated by our servers. It's been founded at MIT, and it actually dates back to a specific publication that I'm going to talk about by Professor Tom Leaton, who's our current CEO, and a guy named Danny Lewin, who came up with the idea of consistent hashing and random trees that the industry took as a standard for doing caching and stuff that companies like Google and others are using. So the sort of interesting things is numbers that we don't claim to have the most servers ever. Google has much more. Other companies have much more. Our pro is that we have it so widely distributed that probably nobody else does, and this is our strength, that we are able to get within the minimal distance of the end user, be it Asia, South Africa, or like different, not only continentally, but also within like ASs and network from the network perspective. So the claim is that Akamai is outputting between 50 and 30% of the World Wide Web traffic. You won't find any like specific source of information for this. It's something smart people at Akamai came up with, but it's sort of difficult to quantify and measure. And I was looking for the source of this information to like verify it, but apparently the whole internet traffic doesn't pass through a central point that you could just tap in and see how much what's on the graph and try to come up with like measures. So this is an approximation. It's peaks cross 10 terabits of per second with millions of hits and some volume of this going through. So the customers that we serve is we have all like media and entertainment companies. We have banks. We have we pretty much using Akamai makes sense for companies which have global reach, have customers and clients all over the world, and are not necessarily looking to build out their infrastructure in every single country they operate in. So about the technical ideas behind Akamai, we don't make a lot of stuff open source. We don't. We have a lot of software written. We're using a lot of interesting technologies, but we haven't decided yet to put them out in the open domain. One of the reasons is that it makes sense at the scale that we're running things, and it's difficult to think people would necessarily utilize something that works on such a distributed scale. In their small open source environments, but we do publicate things. The most pivotal publication was consistent hashing and random trees, and this is I didn't put the date on it, but it's from 1998. You can look them up at this site here. If you go to akamai.com and click about and then technical publications, you'll get a list of some things. So we do publish stuff like scientific papers on our infrastructure, and you can read. This one's like my favorite, because this explains the idea about Akamai, and this is something about I'm going to talk about in a minute. The second one is about the configuration management system. This is like the official name for it. This is something very interesting that we use to manage consistent configuration and ensure safe deployments of the changes we do. And I'll talk briefly about it. And Query is our system for like storing and processing information. This also has this one has a bunch of information of publications on it on this site as well. So the claim from the topic of the presentation I wanted to substantiate. So the internet wasn't really designed to be used like we do it today. There is a legend that when Tim Berners-Lee moved to MIT, they actually met with Tom Layton and talked about the thing that probably internet won't scale as well as we would like it to, because there will be hotspots. There won't be easy ways of solving some of the scalability problems. So the publication dates back to then. It's not like, well, we all know, but to make it like verbal, internet is not like a single entity, and no single entity controls more than 5% of the access traffic. They compete with each other on cost and different things, so it's not a predictable, reliable platform to build things atop. And e-commerce, banks, they want predictability, they want stability. So in the face of like outages, which just happen, the nature of our physical world, the connectivity gets disrupted, and it's difficult to ensure service to your customers that really rely on you. If the cables gets cut, so the claim is that we don't do it like for everybody. We do it for customers who pay us to the scalability, but the service we provide is to the end users. So if you're somewhere in Asia and are accessing a Bank of America site, then we're helping this part of the internet scale by making it available and fast. Congestion is one of the problems that if the traffic goes through some well-connected hotspots, if they get congested, packets get dropped, and nobody cares, because internet is best effort thing. It's not, you don't have a quality assurance. It doesn't scale in the meaning that even if you build out your origin infrastructure, and let's say you've got DDoS attack in addition to your like peak traffic that you expected, it's sort of difficult to get it right. Build out your infrastructure like for some events, then for the rest of the year it may not necessarily make sense. And by building out one point, you have single point of failure. So there are a lot of challenges with scale. Also, this is not to show our portfolio, but we also help with adapting IPv6 by making the last mile accessible via IPv6, even though the backend is done over IPv4. And we also have some products with security, but just to expand on the topic of making the internet scalable and better. So to get down to Akamai, the thing, the top 10,000 feet is we've got a bunch of servers living out on the internet that people connect to basically get content. When you've got the origin infrastructure, let's say there is some consumer site or a bank that you would normally go to. If you go through internet, you using Akamai, you basically are going through a bunch of caching servers, if you will, that provide work around some problems that you normally could encounter, like packet loss. We do things which are designed to actually work around problems like some packet loss or latency by the fact that our edge servers go through, they can go to 3 different rows. One is the whatever BGP would just give you out on the internet, and the other 2 are the routes that go through our servers, our regions with our servers, and this can take multiple forms. One of which is like you would send one packet here, the other packet here, and they're XOR through here. So whenever you get 2 out of 3, you're completely fine, and if you've got 3, then you're better than that, but you don't necessarily need all 3 copies. So when one path is broken, you're still pretty fine. Some things we do, being here, since we are controlling most of the middle path, when the TCP connection is established, because these all are separate TCP IP connections, whenever the middle connection is established, since we are aware of the conditions, because we are constantly monitoring the connectivity between servers, we can do stuff like drop the three-way handshake and limit it as much as we can. And we know the window size, we know the maximum packet and the MTUs, and we can just do it a bit more efficiently that you would normally have out on the internet. So in cases like cable cuts in the Middle East, this is the generic internet connectivity in the region. And by having ways to go around peering problems or like cable cuts, we were able to sustain service. This is like from 2009, but it's a cool curve. So we because we control the midrest part, we can come up with our own protocols to prefetch stuff to make it go faster, like the TCP ops that I mentioned. We can also do like stuff like whenever you're going for the main site, you probably want to go for check the images, so we can prefetch this. Actually, our web server has a powerful programming language, which it's a configuration language, but it's very complicated. So we have people just focused on writing the metadata, as we call it, just to be able to utilize its functions. So things can go in packs and be delivered faster than they normally would. One thing that having such a scale helps in is security. Security meaning in case of DDoS attacks and things where people would either want to download more often than you could serve them, or just people trying to take your site down. Because we are serving like terabits of traffic, this is like right now I'd say large stacks go like a bit further than that, but because we need to have extra overflow capacity for even like software maintenance, we are bringing like a part of the network down to be able to upgrade software. Plus, for attack capacity, we just have enough left to sort of be able to sustain operations and guarantee global reliability, even if in case of a DDoS attack, part of the world, like I'm going to show in a minute, would be overflown. So yeah, this number actually grows, and for our customers, last 3 months, there have been more than 360 attacks, which would be 1 per year if it would be for a full year, but it was like last 3 months, so this is like rising rapidly. The idea is that if we're like normally serving users, we can apply defenses at every point we are in, and basically even if we have a widespread, really distributed denial of service attack, it's not that people are targeting one certain central point. The nature of our mapping system and our distributed platform is that basically people connect wherever is the closest to them. So normally the central point would be taken down, but just because the surface of the attack is so large, it's difficult to take down the whole thing. And even if there is a localized source, it will just take down whatever is the closest, and the whole rest will pretty much function without any trouble. So there are some interesting like stats on attacks for US customers, and I can't really say who are our US customers, but you can just assume some random .gov site. So there were attacks that had some substantial nature for like the parts of infrastructure, and we're using an IP Anycast, which is basically announcing the same prefixes for different places in the world, pretty much like RIPE DNS root servers do. Though we also do it for for our customers and for our infrastructure. So if we see attack being directed from a localized place, we can just announce in the places like closest to this that all the traffic should go to one place. So in cases where we see something going wrong, we can just localize and sync black hole traffic pretty much. So we're getting closer to the technical part, the idea behind the talk. So one thing I wanted to talk about is going to conferences like this. I actually learned how different Akamai is from the world companies that I worked before. A lot of stuff we don't use Chef, we don't use Puppet, we don't really don't use open source stuff all that much. But I think the ways in which we're different helps contributes to your experiences and helps create something interesting, and in some ways maybe shows a different perspective on things. It's difficult to get used to like so many ways down in so specific ways, but it's an interesting perspective. It kind of grew from back in the day where there was just no way to deploy things in a consistent manner, have consistent configuration, and do things at scale that we now are starting to see. So one of the, I think, interesting parts of Akamai is the configuration change, the way we deploy it. We have a automated system which basically takes a file, can do a bunch of like pre-push checks, like syntax checks using like third-party validator for like XML, stuff. It can like push it out to the edge, do file liveness, which is basically if we are requiring our web server to use a piece of configuration, well, is it already there to be used before we actually tell it to? We can do checks on the number of objects changing to, we had a case once when a person mistakenly pressed wrong button in Vim and basically ended up removing not 2 but 2,000 lines from our configuration file. And this was actually after we had the check for a number of objects changing because we were bitten by it before. So this helps save us. What we do is we deploy to a subset of machines. We do it in zones. So we would have the first zone be a small fraction of the network, say below 8%. Then do a bunch of checks. Does the machine is the machine live after we pushed the change to it? And do we actually have a representative sample? Meaning if there aren't even enough machines to tell whether what we're doing is statistically significant, we can just stop right there and say, these are not the conditions the software does. These are not the conditions under which I can automatically, tell whether this is safe or not. It also checks for like, so these are all like, some of them are predefined, you can build up on those. The relative change, like this one would be are there enough machines to actually publish the change and see if it works? This one would be how many machines survived the change. So are machines going down as a result? You check service health. So our service is rolling. Did we cause a disruption that is bringing the site down? What we do for like the web server stuff, because we use it for all kinds of services, not only the web server that we're known for. But for the web server, we would check the response codes. For example, are there the error codes increasing? Are redirects increasing? In case the configuration change the management software sees a significant change, it just holds the deployment at the zone it's in, and basically the alerts fire, and our NOC intervenes and calls people up to check whether what the machine is doing is sane. And you can just, if you know what you're doing, you can just ignore any of these and say, it's fine. It's just that we have a software rollout going out, and it's causing the machines to roll. Also, what we have for some services is self-suspension. Whenever the service considers itself unhealthy to serve, it would self-suspend. So we want to know if the network isn't self-suspending as a result of a configuration change we did. And this is something which is doing a great service for us, because this works for every single request we push, and it's going like working 24/7 without the need of a much intervention. So one cool detail is that we have like 150,000 servers right now, and we manage it with a staff of I'd say 80 people, which is the operations. And some of our customers also have operations in different businesses, but the operations aspect is similar. And we have like guided tours of the NOC in Cambridge and Massachusetts, where we show people the way we have it set up, and actually also do sort of for our customers a conferences of optimization, because we were able to optimize our operations in such a way that we are able to handle like 2,000 servers being operated by a single human being, more or less. Okay, so how do you actually have some automated system know what kind of stuff goes wrong, whether it's safe or not, and on such a scale? Because you may imagine at certain level that there are challenges of scale, and it's not easy to sort of pick a needle from a haystack, if you will. So from 150,000 servers, tell which ones are actually running the wrong configuration, or have inconsistent configuration, have bad disk drives, and all this kind of stuff. We have a lot of components of the system. We have a lot of systems which are like designed to be autonomous, but we need to know how well they're doing. And we need to basically ensure we're controlling the situation pretty much and able to react in real time. So we have something called Query. This is a service which collects data from pretty much the whole deployed network. It has leveling, which I'll talk about in a minute, and so it's tiered model of basically aggregating stuff at the lowest level, and then just making it into hotspots that you're querying. But the cool part is that you can query it in SQL. So it's not really a database, even though it's designed to look and feel like one. But there is no like persistent storage. So whenever you're querying, you're getting what's going on the network right now. You're guaranteed consistency, and that whatever you're querying is not old. When there is no data, there is just no rows. You won't get like trash. So an example of a query that you could write would be to sum hits from all the continents and just group them by continents. So it would use some big tables that we have, group them, just your regular SQL, and you'd have it in two minutes if it's more frequently used tables, and up to 10 minutes if it's some random table like mount points or process memory usage per, every machine in the network. So it's very useful. So the way it works is at the machine level, you would have processes all report to the query process, which would make snapshot every 2 minutes. This is done in such a way that it's easy for developers to write to publish basically stuff to query. You can do it via many interfaces. So an example would be the file system, the reporting, how much blocks are available, what's the block size, and who's speaking, because that's also important. On a group of machines, which we can call a cluster level, it would be like every machine would be reporting their usage. The cluster proxy would add a row for its own and then aggregate the table and make it available for querying. Then the top level aggregators, you'd have let's say per point of presence, you'd have like 10 of those or so. Then the top level aggregators would go down and query all of those, so they know who to ask basically, and it's pull way of getting the information back. Snapshots every 2 minutes, and there is also a static way of providing the information that doesn't change. So like inventory, what machines do we have? It doesn't change because machines go up and down. We need to know what's there and what to expect. So then we can do difference. So we're supposed to have 150,000 servers. How many are reporting in? And we just make a difference between what we should have, what we have, and we have basically alerts based off of it. So we use it not only to like see what's going on in the network, but for like alerting about anomalies and various stuff. Yeah, so this 70,000, I'll need to change it. This is from a publication from, I think, 3 years ago, which is when we had 70,000 machines. The SQL parsers, this is the architecture of the querying and the system. So this box would normally aggregate all the results, and the SQL parser would just process the query. Right now, the machines are combined, so it's one TLA SQL. Because we're publishing quite a lot of data, we have aggregation going on. We have sets of aggregators. So we do it for like different things, like streaming goes one way, has a separate set of aggregators. Web has separate set. HTTPS has separate set, because we also are facing the issues of scale. I'll be skipping since the time is getting short. We have several hundred of these infrastructure machines, and we're using it for making graphs, for making alerts, for making like free-form DevOps stuff. Like if I want to know what versions of software my machines are running, I would just type agg and then write the query, whatever I need to know. If I need to know what the kernel versions are, I can do it via just a command line interface and just query whatever I need. So there is one thing I thought would be interesting would be to show the Akamai platform, and we have an app for that. So there's an app in the App Store on iPhone. It doesn't really work all that well like the internal version does, because here I'll be able to show a bit more if I'll find the mouse. Yep. So these are all points of presence that we have. Yellow would be whenever we're underutilized, I think. Green is okay, and blue is, sorry, it's the other way around. Blue is underutilized, green is right about where we would like to be, and yellow is slightly overutilized. So we have, in Europe, in Poland, we don't have all that much, but most of our capacity is in Warsaw, but for like local context, I always like showing it. And I forgot the shortcut, but you could actually display that. Like these dots represent groups of servers, which are normally like anywhere between 5 and 60 servers that you could call clusters. It used to be that if you were do a mouse over a point, you would get a table with all the IP addresses, the percentages of traffic related to capacity, how much they're serving, and their how many bits, and so on and so on. So we have some places where there are like a bit more machines than Poland, six of us. And you can zoom in as far as you'd like. And these are like all different purposes. This is like our DNS infrastructure, our internet mapping infrastructure, streaming, HTTP, HTTPS. So a lot of stuff here, and storage. So there are like Europe is a pretty well connected place. The US is a pretty well connected place. We have not so many. So yeah, South Africa is pretty okay, though Africa is not a continent in which there is it's difficult as far as the infrastructure, as far as the governments go. We have some issues with presence in China, for example. We have to have like a specific entity which operates there, which is not allowed to be called Akamai. It has to be under special agreements, but we do have a CDN in China that's sometimes facing issue like basically all of our machines that are in China are in like separate DMZ, so to speak, because strange things happen sometimes, like some servers disappear from our network, so the network operations center calls the people right there, and like what's going on? We can see our servers, and they say like, oh, some people from the government came and just took the servers. I'm sorry. We also face some problems in Russia. We were trying to establish presence over there a number of times, and whenever we would send like 40 servers, 32 would arrive, and we would be like, where are 8 servers? And what 8 servers? Then if we would like to have them put in racks and connected, we would have 24. Where are 8? What 8? And down it went. But yeah, and especially like recently with the crisis in Ukraine, Russia said that if there would be sanctions against Russia, they would pretty much claim all the assets of the companies which operate in Russia as their own. So we just proactively destroyed all the secure content we had there, just that we don't sort of run the risk of exposure. So it's pretty much. I think I'll leave time for the questions, but thanks for listening. And if you have any questions, feel free. Oh, we're also hiring, right? So if you have a resume, you can shoot it right here. Thanks.